first practical point. So you see a link here to the GitHub repo with the material, either link or the QR code. There are some instructions in the README to install if you want to follow along with the code examples. So you can install the packages. Small note for people using Conda: if you want to run all examples, you need to pip install PyArrow, because pip already has the latest PyArrow from 2 days ago. Conda not yet. Small note. Normally the binder link should also work if you want to run it online. And if you downloaded the material already earlier this morning, you might need to do a git pull or download it again, because we made some small updates. Then to our slides. Just a quick introduction to ourselves, ourselves. So we are all, yeah, I will do the agenda afterwards. We're all three working at Voltron Data. We are working on the open source side of the company, working on Apache Arrow, mostly PyArrow, but also related packages, nanoarrow, ADBC, Arrow-related open source technology. Voltron Data itself is a company working on composable data platforms, also accelerated by GPUs. That's very, very brief summary. I'm Joris, I'm from Belgium. Apart from Arrow, I'm also one of the developers of Pandas and involved a bit in the geospatial stack, so GeoPandas, Shapely. So that's me.
I can try this one, so you don't have to move. Hello, my name is Alenka. I'm a mathematician, but after a couple of years of using open source tools, not even knowing how everything works, I started contributing to open source with Apache Arrow, which was interesting. And now I'm all into open source, really like to talk about that. So if anybody's interested in starting contributing, talk to me. I'm happy to share information.
Okay, and well, I'm Raúl Cumplido. I'm also an Apache Arrow committer and PMC. I've been involved in the Python community for some time. I was 10 years ago, indeed, in EuroPython on the first very PyCon Berlin, I guess. It wasn't called PyCon Berlin yet, but yeah, it's, you know.
Okay. That's our slides. Maybe just quickly the agenda here. So we will introduce various parts of the Arrow Columnar format, but let's maybe just go to the slides directly. Then I will go there. So you will see here, if you open Jupyter Lab to follow along, there are a few notebooks. I will start with the first one here, intro. So the topic of the tutorial is the Arrow Columnar format. So therefore, very brief, like intro to Arrow itself and the general project. So maybe a question, you can raise your hand if you think you have a very, quite okay idea about what is the Apache Arrow project. A few people, but certainly not the majority. Apache Arrow is also a very, there are many different aspects about Arrow, but where it started, the original starting point of Arrow is illustrated by this figure, and I will maybe zoom out a little bit. It's not too important that you can read what is on the exact boxes. It's also a bit outdated. It's a figure from when the Apache Arrow started 2016, actually not entirely sure about the year, but something around that time. And the problem that it wanted to solve was that, there are a lot of data systems, let's call it like that, that interact or that you have to work with, that all have their own data representation internally, that all have their own conversions to all the different kinds of data systems. And so you have a lot of deserialization, serialization, overhead, a lot of re-implementation of things. And that was like the starting point of Arrow. Let's define a standard, a common way to represent tabular data so that at least we can reduce this overhead, and like if everyone can talk in the same memory format and can talk to that, we can make those things much more efficient to move data from one system to another. That's like the core of Arrow is this format, like how is tabular data, like a data frame, a table, however you want to call it, like, and you load that into memory, how is that like laid out in memory? That's the core of Apache Arrow. That's the columnar format. That's what we are going to focus on in this talk. But the Apache Arrow project also grew into a lot more than that. So in addition to the format itself, there are also specifications about like how can we move this data from one process to another. Like there is inter-process communication, RPC, like protocols. There's also interfaces. How can we share this data within the same process, but between different runtimes, between different libraries? That's something we will show at the end of this tutorial. There have been implementations of Arrow in a lot of different languages of the format. So for all those languages that are listed here, there is an implementation that implements the format itself. Within the Apache Arrow project, there are of course also projects outside of the Apache project itself that will implement Arrow or is compatible with Arrow. But these are the languages for which we, inside the project, we have in implementation, but with varying functionality, because some of those projects, and pyarrow is one of them, also started to have a lot of other functionality on top of just this memory format. So, for example, the pyarrow implementation, which is based on C++, can also read and write a whole bunch of file formats. So pyarrow is mostly used probably for reading Parquet files, or certainly in the early days, in-memory analytics processing, like the Rust implementation, the data fusion component, which is now moving to a separate project, but that was essentially a whole query engine on top of the Arrow Rust implementation. So there is a variety of levels of functionality in those implementations, but the core of it are the specifications, and that's the columnar format. We are going to focus on the columnar format itself. We have a few code examples, but don't expect that you learn a lot of new code today. It's mostly about the mental model about Arrow. The code examples are mostly using a tiny part of pyarrow and nanoarrow just to create an array and like inspect the data that we created. pyarrow is the main bindings to the Arrow C++ library, that the main implementation in Python. In addition, nanoarrow is a newer package, and the main motivation behind nanoarrow is that pyarrow is a big dependency, can do a lot. As I mentioned, it can read Parquet files, it can do CSV files, other org files, read from whole set of file systems, do a whole bunch of compute functions. So it can do a lot, while nanoarrow is really focused. If you just want to receive some Arrow data and import Arrow data or export Arrow data, just around like the memory format itself, that's what nanoarrow does. Just that, and provides bindings in Python, in C, in R as well. So that's the scope of nanoarrow. We will use it because it has some nice functionality to inspect our array to see how it's laid out. Last thing for me for the introduction, so it's the Arrow columnar format. So it's for a table with columns or data frame with columns, but it's also columnar in the way that it's laid out. So if you look here at this small data frame with 4 columns, with some integer, string, and float data type, you can store the way that this data is stored in memory. You can do that in a row fashion, and so many of the traditional databases are row-based, where the data of a single row is stored closely together in memory. But if you want to do an operation on a certain column, that means that it is less efficient, and you will have to jump if you just want to sum all the first column, for example, it's not nicely together in memory, so you have to jump, so it will be less efficient. On the other hand, for traditional databases, which for transactional database, where you mostly want to work on like inserting, updating rows, it can be very nice way to store your data. But a columnar format and most of the more modern data, like analytics-focused databases, but also the data frame libraries will all use a columnar format, and that means that the data for one column is stored together. That's the main idea of a columnar format, and that ensures that you can, what I mentioned before, data is together in memory, you will get better memory locality, you can do like SIMD optimizations to efficient processing. In general, processing compilers work better when data is close together. So that's the aspect of the columnar formats. And so for the rest of the tutorial, we'll go through some of the different layouts, the different types that we have in Arrow and how it's actually laid out in memory. Okay, so then we can go to the first set of layouts.
Okay. Okay, so yeah, we are going to start with the primitive layouts. One of the ideas of the tutorial at the beginning was that even us, Arrow committers, have some problems sometimes to understand how these formats are stored. So it was an exercise of learning how they work, etc. So hopefully we will do a good job explaining everyone how those work. Yeah, I mean, I'm going to start importing, as Joris said, nanoarrow, pyarrow, etc. And I'm going to start with the fixed size primitive layout. Zoom in?
Ctrl-Shift+.
Here, okay. Yeah. So the fixed size primitive layout are representing data that has the same width. So each value has the same width. In this case, we are having a couple of columns here, integer and float. And you can see that, well, integers in this case all occupy the same space and memory. And in the physical layout part, you can see that we have several buffers. That's how we are going to be showing all the different formats. We are going to be showing how these buffers are stored in memory. I'm going to start just with the first column on this case. I'm going to omit the first buffer, which is empty. We will see why this is later. But in the case of the fixed size primitive layouts, the thing is that we only need one values buffer. We don't need any offset. We don't need anything else to represent because we know each value how amount of memory they occupy. On this example, for example, we are going to represent 4 bytes per each value. So in 32s, we create an array, and I mean, we will see that it's an int32. With pyarrow, we can inspect the buffers. I will go a little bit later through how pyarrow and nanoarrow are used. But yeah, here, if we inspect how many buffers do we have, we see that there's one with none. We will see later, but this is a single buffer with all the values there. Yeah, 20 bytes, blah, blah, blah. Yeah. And if we use nanoarrow, we can pick the array and inspect a little bit more, and we can see, for example, that we have a single values buffer with all the data that we created. Okay, how we are doing this with pyarrow and nanoarrow? Well, first, with pyarrow, when we create any type of array, we can inspect the number of buffers that we have, so you can do that with any type of layout, and we will see what are the buffers, their address, and if the buffer is mutable or not on this case. So, I mean, this is basically the same that we were showing before. As we were saying with fixed width primitive, as we don't need to say how much each data occupies, it's just a values buffer, and we In this case, it's just 4 bytes each value, so we know there are 5 values because the size is 20 on this case. Yeah, so yeah, we can see the first buffer again, and we can inspect the value of the buffer. Yeah, as I was saying, we can see that each value occupies like 4 bytes. We can see the values, the 1, the 3. I mean, this is in hexadecimal, but yeah. Yeah, and then the different values that we've created with the buffer. Each one occupies 4 bytes. I mean, it's just, in this case, with NumPy, it's showing on int8. If we say that these are int32s, we just see the same arrays value. Yeah? Yeah, yeah.
So the interesting... Is it on? No. Hello? Yeah. The interesting thing is that the buffers don't know the data type. Right? You have information about buffers, as Raúl mentioned, but you don't know the data type. But in nanoarrow, it's going to get nicer. So the buffer in pyarrow has the basic information, how the length and how much space it occupies. That's it. I think that's it.
Yeah, the difference with nanoarrow, as you can see, is that the buffer knows that it's an int32, because really we are not using a buffer, we are using a buffer view where we also store what is the data type that we are storing, etc. That's why we are using nanoarrow to view, because it's a little bit nicer. Instead of seeing all this hexadecimal with all this padding of bytes, etc., we can see that it's an int32 and that it has 5 values, 20 bytes, etc. So we can just pick the initial data buffer, and then if we pass this to NumPy, we don't have to see that they are int32, because the buffer view already is sharing that it's int32 instead of just 1 byte. Yeah. Okay, so, well, pyarrow has the concept of missing values or nulls, so that's where the other buffer that we were seeing that was null will appear. So in pyarrow we have a bitmap buffer that represents where the nulls are. So in the case, it's an optional buffer. In the case of a fixed width where we have all values, we don't require a bitmap buffer because we don't have nulls, right? But if we have nulls on our column, as in the case on the float, we have this validity bitmap buffer that is telling us on each bit which element is valid or not. The validity bitmap buffer is ordered with least significant bit, so that's why, if you can see, the first bit here is representing the first value. This is a valid value. Second value, third value, or all valid values, and the third value is not valid, it's null. So we can skip when we are parsing the data, or so we know which values are valid or not. As I was saying on the first example, that's why when I was inspecting the buffer, it said that there's, well, on nanoarrow we also already see that it's the validity, but this is none. It's not occupying anything, basically because it's optional, so we are not having this buffer. Yeah, so yeah, we will see it here. We have the floats array, and then when we inspect, as I was saying, we have, one thing, as you can see probably, if you inspect, this is ordered the other way around to map correctly, but in memory we are really storing with least significant bit, so that's why they are swapped in the example. So in memory, if you would go with C++ and see the memory and what is the value of this validity bitmap buffer, you will see this example, but with nanoarrow we are already just swapping that. So in this case it's a single byte, because with 1 byte, as we are having only 5 values on our column, we are already having enough bits to represent what are the values and if they are valid or not. But if we just make this bigger, I don't know, just by multiplying by 2, for example, we have a bigger array, then we will see that it will occupy 2 bytes on the validity, and then it will have, instead of 40, the double, because we will have double, sorry. So in this case, we have 2 bytes for the validity buffer, and we have the values buffer with more values. And we just pad with zeros because we don't care what it's in the end, so yeah. Okay. Yeah, this is the value of the validity bitmap, in this case in hexadecimal. It's two bytes because I increased the values, but yeah. So it's not a small array of 5, it's 10 now, but yeah, that's why it's 2 bytes instead of 1. Yeah. Yeah, so 2 values, the 2 bitmaps, and then I don't know what we had here. Yeah, just the ones and the zeros that we can just unpack the bits from NumPy with the buffer and the ints, and we have to say that the bit order is little, otherwise we should see, yeah, the difference. Okay. Yeah, there are several libraries like NumPy that does a difference between none and null because they don't have the concept or indicator for missing values. As none is a specific value for the floating point specification, that's a difference with ourselves. So if you have a null value in our validity bitmap buffer, you will see that none is already, it's a valid value because it's a valid value on float, so that's why we have, it's still marked as in the validity map as a valid one. Okay, so I'm talking a lot and I'm nervous because I'm not used to do that. You know, I like to be at home on my cave coding, so I think some of you can relate. So I'm gonna go and, yeah, I mean, I would like you to take a look, and I mean, date times are also specific with value, so we don't have to have other offsets or arrays that we will see in the future. So yeah, if someone can take a look and tell me what is the type of the array, or yeah, how this works. There are some hints, but yeah.
And while you're thinking hard and trying out all the things you learned, we have Slido for questions, and we're going to answer them while we have the tutorial, if it's connected to what we're speaking, okay? All the general questions we'll take later, and we'll also find if you just raise your hand and, you know, interrupt us, okay? Because it's nicer that way. We see that you didn't float away and, you know, in the cave in Spain.
Yeah. I mean, Spain is nice.
Spain is nice. So the question, this array, if you run it and you check it, it's a data type. What's its memory layout? Anybody?
It's broken.
Yeah, it's broken in our case, so we need help. Because Raúl changed. How many buffers?
How many buffers does a column date time has?
I hear some typing. I hope it's connected.
Yeah.
Is there any missing data in that array? Because I don't see the whole one.
No.
No
we
missing
have 3
data.
date times.
Okay. So does it have a validity bitmap buffer? No. Yeah.
It's not a type. Dot byte with type.
Well, we're still under the, I mean, a hint is also we're still under primitive layouts. So you have a data type, data time, what would it be similar to? Which kind of type in memory? Yes. An integer, if you have an integer column, it has validity bitmap. If it has missing values, this one doesn't. And a data, right? Okay.
Yeah, so a datetime is another example of a fixed width. If the type contains a byte width attribute, it means that it's a fixed width because we know how long it takes in memory. So yeah, we can have it. In this case, we don't have any none, but if we add a none, then the bitmap, the buffers will change, and then we will have a second buffer with the values. As I said, it's optional. If you have nulls, it will appear. If you don't have nulls, then, I mean, we at Arrow like to save memory. I don't know why. So I guess that's why people like Arrow. So yeah, we avoid having a buffer whatsoever. So yeah. Okay. So yeah. This is probably pretty uninteresting so far because, you know, we have some ints and floats, but yeah, we have things that are slightly more interesting, I guess. Yeah, if we move to variable length, binary strings, or things that we don't have a fixed width, and we don't know how much are they going to take in memory, then we have different ways of saying, okay, how long this string is, or how long this binary is, etc. I think we all can understand how this is going to be. So for us, we store all the string and all the binary together in memory. As Joris was saying, that's one of the things for the column format. So we have to say where the value starts and where the value ends, right? So the difference here, there's some information about what's the difference between a binary and a string. For us, in the physical layout format, you're going to see that it's exactly the same. The only difference is that string are valid UTF-8 binary, so they can be represented as a string. That's basically the only difference. But yeah, that's basically it. So yeah, another example, we have some string data in this column, we have several strings, we have a missing value. So as in general, you will see this a lot. We have the validity bitmap buffer, where we represent which values are valid, right? As we were saying, so the three first values are valid, we have a missing value, and then we have another valid value. And then we have all the values together, concatenated in a single buffer. That's the data buffer, where we have the Python Data Conference Berlin, and then we have an offset buffer. The offset buffer is going to represent where each value starts and ends. So we know that the first valid value will start at 6, at 0, and then 6, and then from 6 to 10, 10 to 20, 20 to 20 because it's missing. So but we still need to have that because the offsets buffer, it's always represented as an int32 in this case. We will see how the large binary strings or the large binary or large string are represented. But we know exactly if we want to go to the X element where it is because we know how many int32s we have to skip. So we see how long it takes, then we go to the values buffer, and we can get directly to the information. I hope it's clear. So yeah, that's an example of binary. As I said, it's exactly the same layout. We are using some strings. We are seeing some hexadecimal because at this point we are saying binary, so we don't know what values they are. But if we show the bytes from the hexadecimal, we will see that it's basically the string. If we directly use the type for a string, we will see the string when we show the representation of the string array. Yeah, the same buffer that we had before. If we see the buffers, as I was saying, now we have three buffers. We have the validity bitmap buffer, we have the offsets buffer, and we have the data buffer. We represent them. The first one, as I said, the validity bitmap buffer. So we know that we have three valid values, one missing value, and a fourth valid value. And if I take a look at the offsets, it's exactly what we had on the example. So we know that the first value is from the 0. It's going to have 6 characters. Here, it's going to occupy. And as we said, this is int 32. Yeah, the values buffer, all the values. And if we spec with the column with nanoarrow, again, we see that it has a length of 5 strings, it has 3 buffers, the validity buffer, where are they, and the data offset, and the data. So yeah. Binary type, as I said, is exactly the same, 3 buffers with the validity bitmap, the offsets and the values, and if we inspect, we have exactly the same. I mean, yeah. Okay. So at this point, can someone tell me what might be the difference between string and large string? I kind of hinted, so. So we have this offsets buffer, which is 32 bits, 32 bits. I was like, for a second, I'm confused. That means that we can represent values up to a point with 32 bits. I think it's a bunch, but yeah. Yeah. So if we want to have data which is larger than 2 gigs, we require the other one because the value is going to be bigger than 2 gigs. So if we want to say that this is coming from this position to more than 2 gigs, we require a large string. So instead of int 32, we use int 64 to represent what the large string here. So sorry, here it's just the normal string. As you can see, we are creating a buffer, and here we are going to create a large string buffer. Yeah. Can also someone tell me what's the difference between these two? What's going to be the difference between these two that I'm going to create? Apart from, I mean, yes, it's going to be int 64, but what does that mean? Lots of zeros at the end. So each one of these values, so this is occupying 1 byte, right, because it's the validity bitmap. This is occupying 24 bytes because it's, I think, 6 int 32, so it's 6 by 4, 24. And this is 26 bytes because it's just the values buffer. Yep. The offset will be twice as big. Yeah, that's correct. Because we are going to be using 64 bits to represent each value, so the offset is much bigger. But we can represent that data, which is, yeah. Yeah?
I have a question. It looks like for the integer types, when there's a missing value, the buffer still reserves space for that value, because the buffer grew even though there was a missing value. But for the string column, it looks like that does not happen because it doesn't have any offset. Does that mean that if you fill in a missing value in a string column, all of the subsequent items need to be copied?
Joris. I'm the release manager. So.
Sorry, no, but it's a very good question. That's one of the things with if you have a fixed width layout, like a fixed size type, like in 64, that means that the length of the data buffer is like predefined. Like you have 10 elements, there are 4 bytes width, so you have 40 bytes. That means that the place where there is a missing value, which is masked by the validity bitmap, still needs to be filled in. And Arrow, like the Arrow C++ implementation and PyArrow will by default use 0, but the specification doesn't specify that. It can be anything. So you will see, I think we saw it before with the integers, or also here with the floats, like the case, like the last 1 bit last value here was none. And when creating that, we filled in 0. It could have been any value. But indeed, it still takes space in that data buffer. On the other hand, for the string data, here, like you have a missing value as well, so it's indicated here by the 0 here. But at that point, it still occupies space in the offset buffer. So in this, again, you could, in theory, you are allowed to put any value that is being masked by the validity bitmap. So in theory, we could have put here like a long string. It would be useless, of course, but that's, so the default that Arrow uses is an empty string because there is no increase in offset. So essentially that means you have an empty string at that place. And if you would view this array without its validity bitmap, then you would have an empty string in that place.
Follow-up question.
Can you speak in the, yeah.
Because of the video.
So the offsets are monotonically increasing, right? So is that a requirement, or couldn't you also save space by actually saving, in this case, 0, 6, 4, 10, like just the length? Ah, okay, but that would be slower because every time you would need to sum, right? Yeah,
I suppose the main reason that we use offsets and not just lengths is that to know the, like if you're the 10th element, you need to know where in my values, my string buffer, then you need to sum the previous values to know where in the data buffer you are. Because now you have a direct index. Like if I want to, like, give me the 3rd element in this array, then I go to the 3rd element in my data offset, and this is the index that I use inside that. So you have a relatively cheap access. You don't need to compute anything except first accessing the offset, like your index, into the string buffer. But for this type of string data, it's indeed a requirement of the specification. The offsets need to be strictly increasing. Or equal for empty strings, but strictly increasing. But that's the next topic that Raúl will continue with. There is also a newer string data type.
Yeah, also you would have to go through all the missing values to find out in which point you have to go to the offsets and then find the value, so yeah. I knew the answer, but I didn't catch the question. So, yeah. So, yeah, we have added some new layouts. For strings, those are used or having used in DuckDB and velox, and we are gonna see what is the difference with the existing strings and why those are interesting. So yeah, we have this example. For example, we have a column here with some strings, and again we have our validity bitmap buffer. The difference with the previous one, as you can see here, is we have a views buffer, and in this views buffer we have several information. For a short string, which is smaller than 12 bytes, we can have the full data on the views buffer. So this is the case for short strings. So for example, in this case, we have a 5 and we have a short here. In this case, we have 12 and we have the short string, right? So if the length is less than 12, we can have the full data on the views buffer. If the length is higher, we are gonna split the information on the views buffer, where we will see what is the length of the string, what is the prefix or the initial part of the string, and then which buffer or which values buffer contains the string, and then the offset inside of the values buffer. So why is this interesting? We can do, for example, if we want to do comparisons for strings, etc., we don't have to read all of them. We can just take a look on if the length is the same and take a look on the initial data. So comparisons are much faster, or the initial part of them, and then we can read the rest of the string if we want to. So it's easier for this type of operations. And yeah. For the values buffer, we can have several. So, for example, if we here concatenate or have a different values buffer. In this case, we are having a new column where we have a new added values. So yeah, we can have different values. So I'm gonna just show it because it's easier with code usually. So yeah, what I was showing, we are gonna see the different. Again, it's the same example as we had before. The column, we have a missing value. If we see the buffers, we are going to see 3 buffers. We are going to see the validity bitmap, the views buffer, and the values buffer. And if we start taking a look at them, again, validity bitmap, I'm not going to go through it again. But then if I see the views buffer, we are going to see the values that I was suggesting. So we have this string is, the first one is 21 bytes. So we know that here we are going to have the first, the prefix for the string. Then it's in the first views buffer, and this is the offset. And then the next one is going to be 5. So we know this is going to be the full value of the, these two are going to be the full value of the string, etc. So if I go and see the views buffer here, as I was saying, the first information, the first 4 bytes, we can see that it's a length of 15. It starts with a string, and then, as I was saying, that's the part where we have the in which values buffer it is represented or is stored, and what's the offset. In this case, we have a 5, and we have the short string already represented, etc. And then, I mean, the values buffer with all the rest of the values there. Yeah. Here we've done a little bit of work. So what we are doing is we are picking the views buffer, getting just the first 16 bytes, which are the length, the prefix, the views buffer, and the offset. And we can see that if we represent the first one as an integer, then the 4 strings, then 2 integers, we can see the values that I was suggesting. In the second case, as we know that it's maximum 12, even though it's length 5, we just fill up with zeros because this was the short string, etc. Yeah. And then if we concatenate an array to the first column as a string view, we will see the example that I was suggesting, that now we are going to have one more buffer, because now we are going to have 2 values buffer, and the views buffer is going to point to the second one. So if I do this with a little bit of magic, we just can see that the first one is just the prefix with what's the value. This is the full value. This is the missing value. Full value again. Just prefix, prefix. Okay.
There is one relevant question in Slido that is asking what happens if I want to change a string in an array. For instance, if I want to concatenate something to one string in the middle, how do you update all the buffers? That's certainly relevant also for this type. So concatenating, like, it's not exactly what is being asked, but what we showed here in an example is actually a concatenation of 2 arrays. And in the case of a string view, we don't need to, like, the 2 buffers that represent the actual string data, like, that will be in most cases occupy most of the memory, can actually just be kept, because the only thing that we need to do is to concatenate the views buffers and ensure that the index the index to, if it's the first values buffer or the second values buffer that is being used, that is updated in your views. But that's a cheaper operation. And so you can see here, so the last string here points to the second string buffer, while the other point to the first. While with the default string data string type that we had before, where you just have offsets and your data, whenever you change a value in there, or you need to change a value, or you concatenate, that means that you always need to copy and combine your full data buffer as well. So the data buffer with all the strings, because that's how this layout works. it's always in exact order of your data. Not only for concatenating, but let's say that you are ordering your data frame and you need to switch orders of values. For this string data type, because it needs to be nicely consecutive, you need to actually rewrite your data buffer with the string values, so they are in the correct order, while in the views case here, you could, you could essentially just reorder those views because they point to a certain buffer and a certain offset in that buffer. It doesn't need to be like nicely increasing order. It can just be out of order, or given that we have we separately store the length and the start in which buffer it is.
What's the purpose of the prefix?
Um,
How can we use it?
The prefix is, as Raúl mentioned, like a typical use case for that is like to shortcut, like a short circuit in like comparison operations. Like if you want to compare, you have two string arrays and you want to check where values are equal, you can because the views are like fixed width, it's much cheaper to access those values. You can quickly check the prefix. If that is not already equal, then you know the two strings are not equal. And it's only if the length and the prefix is the same, then you actually need to look up the index, go into the full string buffer and look up the full string. And that means that you can avoid doing this lookup in your variable length string buffer for every value. That's a typical, like there are other places in other algorithms where you can use the same or a similar trick, but that's a typical example.
I saw is CPU attribute in buffer. Maybe can you give some more details, the difference, how it's stored? Like in buffer, yes, with yes. What's the difference on underlying data structure, if it is true or false?
So the Arrow format can live on any device, so you can have Arrow data on the GPU as well, or on other devices. So this is CPU is essentially that, so meaning that the data lives on the CPU and that Arrow C++ can access the data. Like if you interpret this pointer, essentially what it means that this pointer points to an address that the CPU can address. Because if it would be like a CUDA device pointer, then it would crash if you would try to access that from the CPU. So that's essentially that. So Arrow is not limited to a certain hardware device type, but that's PyArrow mostly works for CPU. Like it has a little bit of functionality for CUDA, but mostly limited to CPU.
And also the layout is the same. I mean,
It's just
yeah.
Mm-hmm. Yeah, it's where the memory address is pointing. Okay. You want to continue? Yeah. Okay. Yeah, so, I mean, this example, as you see, we are creating some binary which are fixed with, and I wanted to, ask the audience if you can tell me what's going to be the difference with the binary or string that we've seen before. Basically, how many buffers do we have? Because we like to see memory here.
assumption that we don't need the offsets anymore because it's a fixed length.
Yeah.
Correct.
Yeah, yeah. So, and it won't have a bitmap either because there's no null value, so it should have a single buffer with the data. So if we inspect, we should see that we don't have, yep. So that's the difference between fixed width. We know that each value is gonna be on 4 bytes, so we don't need the offsets because we know exactly where things are. It's the same as when we are storing ints or timestamps or other information. So yeah. So.
Okay, there are a few questions on Slido. Like we will try to, if you have time in the end, answer more general things. There are a few questions, that I want to answer now. So one question was, what changed with data that it's now smarter to look at columns instead of rows, or was it always smarter, but we just didn't realize it? So that's a question about the row based memory layout or the columnar. To be honest, I don't know the exact history there. I think why databases were using row-based. There are certainly benefits to row-based as well, so it's like for transactional use cases and use cases where you don't necessarily care too much about the analytics performance, like or the typical analytics, like take the average of a certain column, but you're more interested in like inserting, updating things. Then it's there are many good databases that are not columnar. The recent year there is more.
In the past it's now when we are doing a bunch of analytics and a bunch of information with data, but in the past we wanted to just store transactions and new users and what was going on, and storing this data, it was just easier on appending data, it's easier just on a row-based format because we just have to store all the information, so we don't have to regenerate columns, etc. So yeah, that was the initial.
One other question now. So someone asked about, I installed the requirements and the model nanoarrow has no attribute array. That probably means that you're using nanoarrow 0.4 and we need the development version. So in the README there is a line how you can, using a special PyPI index to install the latest nanoarrow.
Okay, I'll continue with nested types. A lot of information till now, huh? Everybody okay? Okay. So if we sum up what we learned, we have the simple things. We have integer types that have one data buffer, and maybe if it's missing, you add the validity bitmap. Then it gets a little bit complicated if you use strings, because then you need an offset to know where it begins, where it ends. But if it's a fixed size, you don't need that again, so we're back in the primitive. And now we get to the nested type. Nested means that there's an object in an object in an object, right? And in Arrow, we introduced this, we use the child array's name and a parent. So we have a parent array that can have one or multiple children, right? And then this child can also have a child array, which are all arrays. Before it was like buffer level, like array and the buffer, but there's like a first array, which is parent, and then it has a child array, and that child array can have buffers also, right? So this is the relationship that we use in Arrow. And also, the parent array is the nested type, but the child array can be a different type. It could be primitive, like integer. It could also be nested. It could also be a type, like a list, okay? So this is an extra thing that we'll learn now. So the first simple case is a list. It's like one, so if we're looking at columns and we have one slot, and in that slot we can have a sequence of values which are all the same type for the whole column, and for the slot. The offset, similar as in the string type, you need the offset to know where one slot begins and where it ends, because the values are stored again together, all together in one buffer in the child array. Does that make sense? Yeah. So you have a parent, which is a list. Yeah. And that list has one data type of the value. So here it's an integer. That's a child array, not a parent array. Parent is a list. And the list only holds the information of the missing slots, not elements in the list, but slots, and the offset where the first slot starts in the child array buffer and where it ends. So the child array will have information about the child, which is, again, a validity bitmap, if in case one of the numbers would be missing, like not the whole slot. And then the values buffer, all the values together for all the sequences, one after the other. So this is the diagram. Is it useful? The diagrams, are they useful? Okay, good. Thank you. Okay. So this is this is how we construct it. Okay, this is how it looks like in PyArrow. So when we inspect the column, the list, what does it say here? Oh yeah, it will return all the buffers. So it has the list has 2 buffers, if you remember, and then the child has also 2 buffers. Okay, so the first buffer will be if the slot is missing or not. The second will be the offsets. The third will be if the individual elements of the slots is missing or not, and then the last one will be the actual data. So, do we have a lot of time? Maybe I'm just gonna skip these things, because we're just gonna, here we take one buffer after another and we kind of put it back in with NumPy so you can see, because okay, buffer address, we don't know what it is, so you can use NumPy to actually get the data in. This is the validity bitmap. This is the offset, which if you check, it should be the same. Did we mention that the offset always has one element more than the column? Did we mention that? I don't remember. Does it make sense why? Yeah, because the end, we need to know where it ends, and it's like one extra. Okay. So this is the validity bitmap for the child, which is missing, so we check if it's really missing. It is. It's none. None means that there's no memory needed for that thing. Okay, and this is the values, and I really like nanoarrow. This is just beautiful. We have all the information together, right? So you can see a list has children, just one in this case, and then you have information about the child, which is itself an array, okay? And one thing I should not forget when we get even more complicated is that even the nested types are columnar. So we don't store, even the nested types are just column by column, okay? All the information, all the data. Oh, exercise. Okay, I think you'll know this one. It's kind of similar than it was before. So if we take this second example, and if you run it and check the buffers, what's the difference between the first, this one? Yeah. So I'm gonna let you run it and check, and have hints. What happens with the offset buffer? So the difference is here in the definition of the type. There's one difference. It's not the same type. It's still a list, right? And also the array is a bit different. Yeah. So the difference between first one and second one, it kind of, the slots look like similar length, right? Is that correct? Am I correct? If I check the first one, like the first one was length 3, then it was 4, and then it was empty. And now we're going to a second version of the list, which would be fixed shape, right? So this one has a shape of 3, so each slot has the same length. And that's how we call it in PyArrow. We say, okay, this is length 3. So if I say, because I like nanoarrow, but this keyboard is new to me. Oh, good. Okay. So did anybody find any difference in the buffers? Nobody. Yes, thank you. Who was that? Good job, thanks. So yeah, it doesn't have an offset because it doesn't need it. We know the length of each slot. So similar than before in the question before, which was great. We have to fill it somehow. We don't need the information for the offset, but then if something's missing, we need to put something there. So the validity bitmap has like too much zeros. And also the data, as you can see, it has 3 zeros there. That means that that's missing. So it's just the default values there. Okay? I think there's another thing I have to mention here. No? Okay, thank you. Thank you, Joris. Joris is our beautiful person. Okay. Yeah? Question? I love questions.
I didn't think it through, but that basically means if I have a lot of null values, the fixed size might be bigger than the variable size.
I don't think, yeah? I mean, yeah. Okay.
Yeah, that's correct. It's a trade-off.
Trade-off, yeah. So yeah, this is our diagrams, representation of fixed size list. You can see there's no offset. And yeah, it fills in the values, correct. Okay, any questions about the lists? Okay, good. List and large list, similar than for the string. If the offset needs to be bigger, you need a large list. That's basically it. So if you check the offset, this is the previous one, and this is the large one. You have just a bigger offset, okay? What's the time? No, I'm gonna skip this one. It's similar then to the string view, except it's for the list. So you can have, so on the left side you have columns, but the buffer, the values buffer, I'm sorry, camera. As you can see, it doesn't really match, right? Oh, thank you. It doesn't match. Do you see? The values, because normally in Arrow, everything that's written from up to bottom, and it has to be consecutive. And here is just mixed, right? Do you see the difference? Yeah. Thank you. So this this list view can give you ability to make out of order lists. You have a buffer and you say, okay, from beginning to middle, I have one slot and then somewhere in between the other one. So again, you don't have to do things with buffers. If you already have something, you can just use that and not make another memory copy. Okay, skipping to struct. So lists, a struct is also a nested data.
Sorry, maybe quick, because there was a question about the lists. Why is it necessary in the offset buffer to start with 0? You can see, yeah, so just whatever,
but
whichever.
The diagram, right? This one, you mean? Oh, the offsets.
No.
Okay, offset.
If you go back, any output that you have there is fine. Yeah, here. So the data offsets always start with a 0. In all our example, it starts with a 0, so can't we just like leave it out? No, because it's not required to start at 0. It's only because the way that we create our data, like with small toy examples, the default it starts at 0. But you can have, like if you would slice your data, you take a slice of a list array. The only thing that it does, it takes a slice of your offsets. It doesn't need to slice the child array. And then your offsets will not actually start with 0. So it's not a requirement. It's just in our examples like that.
It's a good question. So I think it would be worth to have an example with sliced. It was you. Maybe. Very good. To have an example with sliced array, because I think we should know that. Thank you. Struct. Okay, now it's fun part. There's going to be a really interesting example afterwards that you're going to have to help me with, okay? So the struct is a nested type, but like in the list we had a list of values, like a sequence of values. Here you have a sequence of types. So there's a field, a new thing to learn. You have fields, 1, 2, or more, and each field has a child array. Okay? You can have one field here, which is a name. The field name goes into the schema, which is a description of your data structure. It's not in the buffers. And the values of that key, so the values of the array, go into the buffer. You can have multiple ones. So this example is, oh yeah, there's any child array? Oh yeah, the child arrays, yeah. So here we have 2 fields in this example. The child arrays are separate buffers. So if you have 5 childs, they have separate buffers. They don't have to be together in memory. Okay, and all the values for each field need to be the same. So if you have 2 fields, here is a string. They all have to be strings, all the values. And the same for the second, which is ID. So the struct, this example, so the parent type only has the validity bitmap, no other information. All the other information is stored in the child arrays. So here, this struct has 2 children arrays. One is a binary string, and the other one is fixed site primitive, which is just integer type. I think that's enough of information. You can have 3, 4, 5, so it will all be stored like a field as a name, and then the value as an array. Does it make sense? Is it clear? Okay. So here, this is an example of the construction of this diagram's data. This is how it looks in pyarrow. So the buffers, again, you have struct buffer, which is the validity bitmap, and then you have 3 buffers for the string type and 2 buffers for the integer type. A lot of buffers, okay? And if you use nanoarrow, it's a really nice way, isn't it? Like, it's really clear. You have 2 children, first one is string, and the second one is integer. It's really clear, with all the buffers listed. Okay, this exercise I like this exercise. You have to create this, this nested example, which is a struct of a list, and a struct of a list of a string, and then the second field is a list of a fixed size list. Okay, it's nice. You can get creative with these types in Arrow. And my question is, this example, how many buffers does it have? And I will wait for the number. How much time do we have? We have 20 minutes. And I mean, Joris is still up. It's worth listening to Joris, so you should be quick. And we'll go together. Just like, if somebody has any idea, you can help yourself with some code that you learned. Oh, the hints. Yeah, I'm sorry.
No, I just want to show the type.
That one. And the hints. We have hints. This is so easy with the hints. Isn't it? I mean, you can use buffers method and you just list them and just count.
Yeah, they asked me this morning and I got it wrong.
Anybody just a number, or we should go together? I don't give out beers. I don't know if... Yes? 11. Bravo. Yes, 11. Very good. 1 for the struct, right? And then you have the first list, which has validity bitmap, offset, and 1 child array. The child array is a string, right? It has a validity bitmap, an offset, and a data buffer, which we are at 6, which is the struct and the first child. And then the second child is a list, which has a validity bitmap, an offset, and a fixed size list, which is a validity bitmap and a child, which is an integer. But it's a simple integer with only 2. I don't know why. I don't know why I counted.
You said child.
Okay. So it has 2 validity and the data, final data. 11. Very good. Okay, so we're at the last. Then I'm off to have a nap, but we're at the map. A map is, it's interesting. It's similar, I mean, it's, to me, I needed some time to have a real clear difference between a map and a struct. A map, so here what it says, represents nested data with key value structs. So you have a variable number of key value pairs. Example, on the keys are movies, Dark Knight. This is actually not my example. It's from the doc strings that somebody contributed. Thank you very much. Really good example. So the movies, and then this is the keys, and the values are the ratings from 1 to 10. So the difference between the struct and the map is the first thing, the struct names are saved in the fields. This is the keys, which is in a schema. In a map, the keys are a separate array, right? So this is Dark Knight, it's all one array of keys. In the struct, the keys are field one key, field 2, second key, and they can just be string because it's a descriptive, it's in a schema. In a map, the key can be a number, yeah? It can be string, it can be whatever, okay? And the values are also a separate child, just like the map. It can be a string again, it can be an integer, but all the same type. So value has to be one type, and keys has to be the second type. And another difference is, as you can see, a slot can have multiple elements, yeah? A slot. But it can only be one key array and one value array. Because in a struct, you can have multiple fields with multiple values, with multiple child arrays. Did I do well? Kinda?
You did great.
Thank you. So, a map has always two child arrays. Struct can have 10 child arrays. A map always have 2 child arrays. It has a key child array and a value child array. And this is the example. Okay. You can run this, you have the notebooks, you can run this yourselves. We added a comparison of how the struct and map converts from PyArrow to Python, because it's not really easy or simple to understand. Just run it, there's descriptions. Does it become a dictionary or a list of tuples, or what does it become, and what are the options to convert that? So have a look at that, and I'm gonna leave it to Joris. Thank you very much.
So there are coming in a whole set of questions. I will try to answer some of them at the end. Or also already some of them answer in the last notebook. But so we have seen different layouts, and we have seen in the primitive layout, we have seen some example of types using those layouts. But there, yeah, that's only a subset of Arrow that we have seen. Yeah, this diagram will not be very readable in the back, I think, and zooming in also doesn't help because it scales again. But I will do my best to quickly explain it. So this diagram has an overview of all the types that are using a certain layout. So we have seen the fixed size primitive layout, so just one buffer of data, and you know how many bytes each slot takes, so that are typically the numeric data types that we have seen, like int floats. Also some others, like temporal types, like timestamps, dates, times, duration. Those are typically stored as integer values. In the case of timestamp, for example, it's like the number of seconds since 1970, and so it's stored as an integer. And that's also, and that is using the same layout, physical layout in memory as an integer array. Same as for the fixed size binary. Decimals is also fixed with a certain byte width. So in this case, there is a version with 128 bits or 256 bits. Bool the same. The only difference there, bool is also a fixed width, but bools essentially just use the same idea of the validity bitmap, so it's just bits. So, for example, in NumPy, a Boolean array is a byte, like is 1 byte per value. The Boolean array in Arrow is 1 bit, using the same logic of the validity bitmap. So for example, a bool array with missing values has 2 bitmaps, essentially, one the validity bitmap and one the data buffer. There's also a null layout, which essentially means there is nothing. It just stores how many values are in that array, and they are all null. Won't go into detail. We have seen the variable size binary layout for strings, for binary and string data, and then the newer variant for this with the views instead of the offsets. Then we have seen all the nested types. So we have seen lists, fixed size lists, a version of list view, the struct. A few of the types that we haven't seen are, there is also a union type with its own layout. What is a union? Essentially, it's, I have an array and I know that it's either an integer or either a string. It's one of the two, and so it's like an abstraction around that. Essentially, what it does under the hood, it stores all the ints, all the strings, and then it keeps track of my first element is a string or my second element is an int, and that's the way that it stores like a union type. The map that we have seen, which essentially under the hood, it's not a separate layout, so it doesn't really fit in the diagram here, but because it's actually just a list layout with a child array being a struct. Dictionary and runtime encoded are essentially 2 types that I was thinking I can quickly show the dictionary encoding. So in this case, there are also nested types because they have a child array, but they, because of the encoding, they can do some compression, like some size reduction of your data. So in the case, like dictionary encoding is used if you have a lot of repetitions in your data. Let's say I have ABA, so a string array, I dictionary encode this array, encode. So this results in a dictionary array. And then a dictionary array, what it will do, it will store the unique values separately in what it calls a dictionary, and then the actual data, so which has the same length as like 3 values in this case, are then indices into that dictionary array. If I would look at this with nanoarrow and inspect it, you can see how it's laid out. I didn't import nanoarrow here. Arrow as NA. So you can see that the data itself, the buffers of the data itself, you have the validity and the data, which are my indices, and it has a separate concept of a dictionary, which is the child array. But it's, yeah, in the format, it's a dictionary is a separate concept from a child array, although like logically it's very similar. It just stored separately in the, or mentioned separately in the layout. So that's dictionary encoding. Run-end encoding is essentially if you have a lot of repeated values that are next to each other, you can say like I have like 1, 1, 1, 2, 2, and then you just say I have 1 3 times and then 2 2 times. Essentially, that's another way to encode your data. That are all the built-in types. Maybe you have, like, you want to define your own type if you have some application-specific logic. And Arrow also has a concept of what it calls extension types. Extension types are nothing more of, I'm going to use one of the existing types, but I'm going to add some custom interpretation. Like I have integers, but I know they represent, yeah, something else. Essentially, like a timestamp are integers that represent the second since 1970, for example. And you can have your own custom interpretation of the data. Examples are like UUID. You would store it as like fixed size binary, but you can annotate that type as I know these are these bytes should be interpreted as a UUID. Some examples of built-in extension types. So there are certain extension types which are like standardized by the Arrow project itself, and they are called canonical extension types. And that are the fixed and variable shape tensor data. And currently there is discussion about also standardizing this UUID and standardizing JSON as just a text blob, but where you know that the text represents some JSON value. There are also a few community extension types, and one of them where I'm involved in myself is GeoArrow, where we are going to represent geometries in Arrow format. And essentially what you have here is, you have different ways that you can represent geometries, but in the end, a geometry is like you have a point, which is an x and y coordinate, and you maybe have a line string, which are a collection of points, and you can, in the end, store this data very easily with Arrow using, like, you store your x's together, you store your y's together, but then you can use like a list of lists to determine I have a polygon which has rings, and each of them is a list of like, you can make very nice use of these nested data types that we have seen. A question?
Is that implementation, will that be not compliant but compatible with well-known text formats?
The GeoArrow, so the GeoArrow project has some library, like packages that implement conversions between them. It's like well-known text is a different way to represent, so you could also store your geometries in like a text in a column of strings. But that means like the main advantage of like the native Arrow, like the more native Arrow way, is that if you just want to access the coordinates, like you want to know the like what's the min and max x and y values, for the text one you need to parse your text. While in the case of the Arrow, using like a nested type of just floats, whatever nesting you have of a list of a list of a list, your final x and y is just two arrays. I have one array of all my x's, one array of all my y's, and I can just calculate the min and the max of both arrays. So you get a very nicer layout to actually compute things on than something like well-known text.
The idea would basically be to just use well-known text to get the data into pyarrow.
Yeah, that's certainly possible. A last thing, I don't have much time anymore, but I want to address a few questions as well that were related to this. So in the examples, we have often been like passing some, like created some data with pyarrow and then passed it to nanoarrow to inspect it. There have been questions about like, why do we do that? Or like, which one of the two should I use? Is there a conversion happening? So maybe just checking the questions again. So the first thing is nanoarrow is a very small library and only deals with the format. So if you, for some reason, like you receive Arrow data from somewhere and you just want to, for your own application, I want to get the buffers, I just need the memory address so I can pass it to some other C++ or Rust function that just needs, here is the data, then nanoarrow is sufficient and you don't need to rely on something like pyarrow. PyArrow comes with all that additional functionality. For most end users, PyArrow is what you should use. The reason that we use nanoarrow here is because it has a bit more, like, because it's lower level, it shows like the real like layout of your data, which for the purpose of this tutorial was actually useful. Most end users will want to use pyarrow. We have been passing nanoarrow or pyarrow data to nanoarrow, or it could also be the other way around. And that actually happens just zero copy. And that's not only for pyarrow or nanoarrow, but that can happen, that works for any library that implements what is shown here, the ROC data interface. And that's part of the Arrow specification that allows libraries within the same process to just share data, because all those buffers are predefined how they are laid out. you can just say to, like, I'm a Python library, and I say I can pass to a Rust implementation of Arrow, like, here is my buffer, here's the memory address of my buffer, it's this length, it's that type, and they can just interpret that data without any copy. And that's when you pass data from pyarrow to nanoarrow, or the other way around. They will just share the pointers to the data and the data type, and they know how to interpret it without any copy. So that's the C data interface. This is not specific to Python, so it works with any language that can implement a C struct or a C form function interface. I don't have time to go in detail here on the actual struct. So, but essentially, you will recognize things that you have seen in like the nanoarrow. So you have an addition, like you have the buffers, children arrays, and also the length and null count. But yeah, essentially the buffers and the children arrays. I had a small example here to show that it's actually zero copy. It's something you shouldn't do at home to mutate buffers under the hood, but to prove that it's zero copy, so I create a string array with pyarrow. I pass it to nanoarrow, and you can see now it's the same strings, but it is actually zero copy. To prove that, I take the string buffer, so the third buffer of my pyarrow array, I convert it to a numpy array. This is something that also happens zero copy because of the buffer protocol of Python. Then I mutate my buffer, the string buffers, and it's in bytes. So I'm converting here an exclamation mark to the interior representation of those bytes, and then you can see that the first 4 bytes of my pyarrow array is now exclamation marks, and the nanoarrow array has the same mutation. But yeah, certainly don't do this at home. That was our material. I don't know if I'm allowed to answer a few more questions or if we have to stop.
Maybe we do 3 more minutes, so pick 1 or 2. We have 12 questions. We will not be able to answer them all. Let's do 3 more questions, and then we end. Please keep seated, and then we go for coffee, okay?
Yeah. So I will then just go from like the most voted. Is Arrow supposed to replace Parquet? No, is a simple answer because it's 2 different things. Arrow is the in-memory layout. Parquet is an on-disk file format. There is some confusion because you can also dump whatever Arrow has in memory to disk, and you also have a file format. But the Parquet is like really optimized, like for with a whole bunch of encodings and compressions to have like efficient on-disk storage as small as possible. That's not the use case of Arrow, but they work very well together because, like, yeah, when reading Parquet into memory, Parquet is also a columnar file format, has more or less the same data types as Arrow, so it matches very well together. When working with data in an Arrow backend, does Arrow automatically choose the best representation, for example, for strings, by looking at the content? Arrow itself doesn't do that because Arrow is also, like, there is no such thing as Arrow as an implementation. You have separate implementations, and I can answer that question from pyarrow point of view, and pyarrow doesn't do that. It will not, so it has a certain default string type. Like if you don't specify the type, you will get the string. And you can ask for a string view. But I would say in general, this is pyarrow wants to be like a low-level building block, and it's the application. Like if you would build a data frame library on top of pyarrow, it's them that could decide, like, okay, I see the user has strings. Maybe in this case, I should rather use like a string or a large string or a string view, and they can hide that complexity. pyarrow itself doesn't do anything smart except like infer the basic data type. How much more space efficient is Arrow format compared to others? Yeah, I'm not super familiar with other formats in the same space, like, or other data system or databases that have their own formats. I know that, for example, like the newer data engines like DuckDB had their own string view because it was more efficient, but that's now being adopted by Arrow as well and being standardized. And maybe the last question, is there any way that one could pass the Arrow memory pointer to another process? So that's not possible, but it's actually possible to pass it to a Java. So within the same process, you can use a CData interface as well to pass data to Java or like to the JVM within a Python process. But to actually another process, we typically have the IPC protocol where you have one serialization step. But because it's all like the data, how you pass it over the to the other process is exactly the same layout as it's in memory. It's very cheap. Like of course, you need to do a copy to send it to another process or to send it to another node or cluster or another machine over the wire. But because it's exactly that format that you send as it's loaded into memory, you get a very performant way of sharing data between processes.
Very good. Thank you, Alenka, Raúl, and Joris. Let's give them another round of applause.